Welcome to another exercise on the Simplex algorithm. As exercise, we have here simply, by using the Simplex algorithm, calculate the optimal solution to the following linear problem. The problem is a minimization problem of the objective function 2x1 plus 3x2 under the constraints 2x1 plus x2 should be larger or equal to 9. 4x1 plus 5x2 should be larger or equal to 20. And 2x1 plus 8x2 should be larger or equal to 16. Finally, last constraint, 5x1 plus 6x2 should be larger or equal to 60. And of course, we have our non-negativity constraints. So to solve this problem, we first have to transform this problem into a table in which we can work with our Simplex. So that's what we're going to do first in the next slide. So I'm going to switch to a new slide, and then I'm going to put this mathematical problem into a working table. For this, I consider that I have two decision variables, x1 and x2, and for each decision variable, I'm going to select or introduce one column into my table. Additionally, I introduce one row for the objective function and one row per additional constraint. So I have 4 constraints, so I get 4 new rows with one additional variable each. This gives me more or less the structure for the table I'm working with. Now I have to insert my coefficients and right-hand values into this table. For this, I'm going to start with the objective function. Since it's a minimization problem, I can take the coefficients from the objective function as is. So for x1, I take 2. For x2, I take 3. Then I'm going to insert 0 for x1 and x2, since they're both up here, giving me as a solution a value of 0 for the objective function. So this is the first part. Then I'm getting to the constraints. All the constraints need to be smaller or equal to constraints, which in all 4 cases they are not. So I first have to change all these constraints into smaller or equal to constraints. And I can achieve this by simply multiplying each of those 4 inequalities with -1. So in other words, not only will it change these signs, it will also make all the coefficients and all the right-hand values negative. So for x1, for the x1 column, I get here not 2, 4, 2, 5, but the negative values -2, -4, -2, -5. And for the x2 column, I get -1, -5, -8, -6. These values here. And finally, for the right-hand side, I get -9, -20, -16, or -60. These values here. So with this done, I see that I completed this first table. Now I have to check whether my solution is actually feasible. For this, I'm going to take a look at the values here on the right-hand side and check whether they are all positive or 0. Well, in this case, neither of them are, so I do not yet have a feasible solution. To find a feasible solution, I'm going to start by selecting this row where I have the largest value here. So in my case, I'm starting with -60. Then I'm going to select in this row one value which is negative. Well, in this case, I could select both, and where up here I have a positive value ideally. Well, again, I could select both. And then I have one potential rule where I just take the quotient of these values. In this case, I would have 2 divided by 5 and 3 divided by 6. Usually, I should take the larger one. So I should take -6 as pivot element. But since I already know the solution, I would know that if I do this, I have to do 2 additional recalculations. So to make my life a bit easier, I'm going to go with this. So not necessarily does this rule always select the largest version, give you the best result in the fastest way. But if you want to have one rule, that's one way to go. Well, in either case, as I said, here arbitrarily I'm selecting -5 as pivot element. So I'm going to do my rec transformation with this pivot element. And in this regard, I'm first going to switch these 2 variables, x1 and x6, because they are in pivot row and pivot column. For the pivot element itself, I'm going to divide 1 by the pivot element, giving me -0.2. Sorry. In the pivot row, rest of the pivot row, I'm going to divide everything by the pivot element, so by -5, giving me here +1.2, and here +12. In the pivot column, I'm going to divide everything by minus the pivot element. So in this case, by +5. So I go 2 divided by 5, -2 divided by 5, -4 divided by 5, and -2 divided by 5, giving me these values here. Then, in this regard, I'm going to do all the rest of the values, but I'm going ideally to start with these 3 values and then with that value, because this way I can check whether I'm already at a here feasible solution, if all of them should turn out positive, and here whether I'm at the optimal solution. Since they are not in pivot row or pivot column, I have to use my rectangle form, meaning for the 16, I'm going to form a rectangle which has the 16 on one corner and the opposing corner being the pivot element. And then the calculation form is this original element minus this one times this one divided by pivot element. So here I have -16 minus -2 times -60 divided by -5. So I have minus, 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 4 minuses. They're all canceling each other out, so I have plus. So I have, in other words, 2 times 60 divided by 5, or in other words, 24. So -16 plus 24 gives 8. For this value here, this would be my rectangle. So again, -20 minus -4 times -60 divided by -5, giving me, in this regard, minus, 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 4 minuses again, so again plus, so -20 plus 4 times 12, because this is 12, 4 times 12 is 48, so -20 plus 48 is 28, this value. For this -9, have this rectangle, so go -9 minus -2 times -60 divided by -5. Again, 4 minuses giving me plus, so -9 plus 120 divided by 5, which is 24. -9 plus 24 is 15. So I see here in this case I have a fully feasible solution. And if I also recalculate this 3 here, I would have 3 minus 2 times -6 divided by -5. So minus, 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 3 minuses, 2 cancel each other out. So it's still 3 minus 2 times 6 divided by 5, which in the end will be 0.6. So with this, I see I also have 2 positive values here, meaning my solution is feasible and optimal. And I could more or less stop at this point, but I will need here the new value for the objective function. So I have to consider this part as well. So this is 0 minus 2 times minus 60 divided by minus 5. Minus, minus, and minus again. 3 minuses, giving me minus 24 in total, which is the value here. Well, we could also calculate these three values here. This would be then for the minus 1, this rectangle, for the minus 5, this rectangle, and for the minus 8, this rectangle. But with this table, I have arrived at the optimal solution, which is also feasible, or the feasible solution, which is also optimal. And I can read the values for the objective function and for my decision variables from this table. Everything up here has a value of 0, so x2 will be 0, and x1 will have the value on the right-hand side. Like all of these variables, they get the values on this side. So my optimal solution will be x1 equal to 12, x2 equal to 0. And then my objective function will have a value. Well, this is slightly different because it's not minus 24, but plus 24. Just since I have a minimization problem, I also have to change the sign here again. So we'll have here optimal value of the objective function of 24. And well, this already brings me to the end of this session. So I hope you enjoyed it. I say goodbye and see you next time.